So good morning, good afternoon, everyone. Um, so today, like as usual, this meeting will be recorded. So if you want us to edit something, please reach out before the end of the meeting. Today we are planning a discussion on uh, and some first order analysis of the mesoscope data, especially relevant to QC. And Davis agree to present what he has done. But I think it's still early. I thought it would be helpful to bring back the paper just to provide context. So in the last week, I had it with data tables that a summary of mice and session. I still draft, but second version list what we did for different types of modalities. And then the question, so we,
Oh, I think you're muted.
oh, I'm sorry. Was it
It was
speaking
only like the
alone for a
last five
minute?
seconds. Yeah.
Or, or just stop in the middle?
Yeah, I'm not
Can
sure.
you hear me?
I
Yeah,
can hear you now. Yeah.
yeah. It was just a couple of seconds.
Oh, really?
Yeah.
I don't know how it happened. What we want to, I think, discuss today is this figure four, which is SNR, response amplitude, unit extractions, or potentially metrics for mesoscope, and this would translate to other modalities. So I think we should keep in mind whatever you're showing today, Davis. How can we apply it to other modalities so that it's consistent? Um, okay. Do you want to share your screen or?
Yeah. Uh, all right. Can you see it? Should be
Yes.
okay. Yeah, so the three sort of metrics that we kind of came up with in collaboration with my PI, Dr. Najafi. One is sort of a sustained exceptional event score, which she used in her postdoc, and I think there's a reference later in the notebook to a Cayman paper that it came from, um, and also sort of a more standard, just 95th versus 50th percentile SNR score. Um, and then in addition to those, not exactly, directly an SNR metric, but more of a looking at the events that come with the DFF traces in the data, looking how closely those fit an exponential distribution and the noise outside of them are is a Gaussian. Um, so if that's, I think the first two, I think were definitely what we're looking for, and the second one or in the third one, I'm not entirely sure, but I know that's sort of like something we look at in our lab when we're looking at whether our events seem reasonable. Um, so I kind of have like a more detailed step by step of how each metric is calculated here. If we want to go through that, or I could
Yeah,
just
maybe can you explain the exceptional event score? I don't think I've encountered
yeah.
this before.
Okay, yeah. So this one is more, it's sort of asking the given this trace, is there at least one event in the trace that seems to be highly unlikely to be due to noise? Um, and so it calculates the half sample mode as the baseline for this. So basically that sorts all of the values of the DFF and then sort of finds the narrowest interval that contains half of the samples and then sort of the densest uh, part of that. It keeps repeating that, and then gets you a central measure. And I think that's because the reasoning is that the mode is going to be more, well, I guess that like an event score that's above the baseline is going to bring up the median more than the mode, if the mode would be more representative of um, the actual baseline noise. Um, and so it kind of assumes that, a noise model um, for that uh, um, the baseline mode, but it only takes into account the values below it. Um, so I guess it's, assuming that we want to know the or the fluctuations above the mode would be responses to actual stimuli or um, uh, we basically want to like take those more seriously, I guess, since they're likely to be the actual events we're looking for. And so then it looks at all of the positive deviations in a row, and kind of gets like a consecutive um, negative log probability and just adds that together. And then whatever the largest value that it gets, um, it will save that as like the exceptional event score. Um, so yeah, it uses the sliding windows to get those adding up those like negative log probabilities. And so basically it's even if you have like an ROI that's, I guess, potentially has a lot of noise, could it be at least useful? Is there at least one event that seems like it could be useful for um so it's a little unconventional, but I guess it kind of gets it. I know in a past meeting there was kind of like a discussion about um you know how do you quantify SNR or like usefulness of a metric, because someone may only need one ROI, or they may need, that may be for what purpose they're using it. It might be um, fine. Um, so I guess that this is kind of meant to be like this ROI has at least one event that could potentially be used. Um, so I can go into the next one, or if we have any more questions about that. Um,
That makes sense to me.
okay. Um, and then,
Sorry, Joe, I just
yeah,
wanted to add, sorry I was late, I was at another meeting. So this method, I believe Davis gave the introduction. So this is something that Andrew Giovannucci, you know him, so developed when I was together working with him on some project in my PhD. I applied it on in my postdoc. So I applied it on my postdoc data and did quite some tests at the time, looking at high, low, and things made a lot of sense. So that's why I told Davis to try it here. And this is also in the Kaiman paper. So yeah, so I don't see why this should not work on another data set, but hopefully with the plots that Davis has provided, we can see if that's a good one.
Yeah, I mean, the only thing I could think of is whether these behave very differently with inhibitory neurons.
So I
But I mean,
used it
but
on
I'm
both.
guessing you use it, right?
Yeah, I used it on both excitatory and inhibitory in my postdoc,
That's
and it
right.
made sense. Yeah, yeah. And it was on PPC, so yeah.
Maybe it's a good candidate. Yep.
Yeah.
cool. Do we want to jump to the plots for those while it's still fresh, or do we want to just keep going through the metric definition?
You decide, Davis.
Okay. Well, I think these will be a little bit quicker to explain, so I guess I'll just keep going through. Um, so the 95th, 50th robust SNR. So in this, we're just calculating the median, the 95th percentile, subtracting that, then doing a Gaussian smoothing to get our residuals by subtracting those from the original values, get the median of the residuals, and then it's called, I'm just using robust noise here because of the using the median absolute deviation. It's supposed to be more robust to fluctuations than a mean, and or large outliers, and then storing that, and then the higher values means that we've got a larger upper tail of the DFF trace relative to like the faster things that would be explained by subtracting the residual from, or the smoothing from the values, the original values. And yeah, I guess if we have any questions about that or no.
I mean, to some extent, it's going to give similar answers, right?
Yeah, I think the main difference between this one is it's more of a signal, or it's a more of a full recording measure because it's sort of you're capturing over the whole recording, versus the other measure is more of like you're taking a max within within the sliding window, and then that's your measure for that whole thing, if that makes sense, for that whole recording. Whereas this is like taking an aggregate statistic over the whole recording. So yeah, I guess one could be like, you might have different measures of this for different slices of the recording. Where, yeah, sorry. So, does that answer that?
Yep.
Okay. And then the Allen event. Okay, yeah. So this is just for the events that come with the DFF data, which I think it's using sort of like a similar deconvolution method as like OASIS, with some modifications, but it's largely like that kind of method. So there's the underlying assumption that you've got these Gaussian noise and sort of an exponential decay of your underlying spikes. So this just basically tests how close the events that you found, if you match the DFF around those events, how close do those match those assumptions, in terms of getting Gaussian noise and an exponential fit. And it uses Kolmogorov-Smirnov. So I actually found out about this test from AI, but it's basically you get a CDF of both of the just your theoretical distribution and then your observed distribution, and then you take the max distance between those CDFs to get that, and that gives you your KS score for that event. Or yeah, and so yeah, so a high value means that it looks well behaved. Oh, one thing I also forgot to mention about this measure, the sustained exceptional event score, is that the raw output of it is like a negative because you're summing negative log probabilities. But in the plots, we take that negative probability and negate it again to make it more easily interpretable. So the higher, the more likely. It's that event. There's a non-noise event. A lot of negation there. But yeah. So any questions about the Gaussian score?
Davis, quickly go to Alan.
Yeah.
So the high value here means that, right. So
Oh yeah, so it's one minus the mean. Yeah, the mean, sorry. Yeah, because the higher the KS statistic, that means actually the bigger the distance between your observed and your theoretical distribution.
so kind of similar
Yeah.
to what we do with be 2p, that the residual should be Gaussian. It's the same concept, but for Allen, the convolution method.
Yeah.
But are you really assuming Gaussian distribution as the base?
Oh, I think it's a exponential for the um for like the calcium decay, but the noise outside of it is Gaussian.
I see.
Yeah.
And Jerome, for the data in my lab, it works very well. Like Ali plotted the ones with the neurons that match, the residuals match a Gaussian noise, and you can see that they're actually the better ones. Yeah, so we'll have to check it.
Okay. All right. I guess now I'll start getting into the plots themselves. Here we just have, this is the session that we used from February 20th of this year using all the planes. And then I've sort of set it so that later on we can incorporate more sessions into it, but for at the moment it's just this one session. So for this session, we can see the exceptional event score distributions across all the ROIs. And I think there were, how many were there total? Let me see. So I don't think I have the total across all planes, but I do have the amount of ROIs.
And this is tested on one session, all of these?
Yeah.
Just
Mhm.
one.
Yeah.
And in your plot below,
Yeah.
so I'm assuming it shows the deeper plane as a lower number and the superficial plane as a higher number, as you would expect.
I think so. I was just using the labels that came with the
Yeah, but I guess that's a
data.
good sanity check.
That's right.
Yeah.
Because one could say, I'm going to decide, to count the number of units that are above a certain value and say I see that many neurons that are higher than X number across all planes, all sessions. So you know what? So you could decide. You could use the metric to uh, sort of set a comparison across the sessions.
I see. Sorry, I think so you're saying the
Well, because as I understand, this tell you how strongly the biggest event compared
yeah.
to the noise, right? As
Mhm.
measured by the metric. And so if you have a really high score here, it means the events that you detect are very easy to measure. And
Mhm.
so if you were to set a threshold, you could count how many neurons above a certain number of above a certain threshold are for each plane or each sessions across the data.
I
And then
see.
as a result, you could start to sort of get a sense of quantity,
Yeah, I
how
see what
good
you're
is
saying.
the whole data set, which I think which is what we're trying to get at is how the data is distributed across the entire set.
That makes sense. Yeah. Yeah. And I do a little bit of that of like at the end of the notebook. So basically creating like for each of the metrics, basically partitioning them into thirds and
Oh,
then having like a bin for like a low, medium, and high bin with like a 20 randomly sampled DFFs um, to look at to see if there's, does this metric seem to be showing us some kind of systematic difference just from like a bird's eye view of looking at the shape of the DFF
yeah.
after yeah. Um, so yeah, the similar SNR. Yeah, sorry.
No, sorry, I just wanted to say, let's look at this carefully, because I think this the drop with weight is a good sanity check. So I'm trying to see if your other metrics are capturing that as well. So the 95.50, I just meant don't move quickly so we can see that. Yeah, more or less it's there. I thought what Jerome, maybe I got it wrong, but I thought what Jerome was saying was that you want to see within a session how it changes. Like if within a session the quality drops. Is that what you were saying?
Oh, no, well, that's one thing that is very variable across time.
Yeah.
Yeah. But I also think across session, because
Sessions, yeah.
the goal of the data
Yeah.
release paper is to get a sense
Yes, that's good.
of quality in multiple directions.
Yeah, but what Davis said is different. We can talk Davis later about it. What Davis has done is to visualize it so we can evaluate it. So
Yep.
basically we can actually by our eyes evaluate the metric, but that's
Can you go back up?
Yes.
Yeah, I'm just looking at, so the distribution on the left is across all ROI. It's very skewed.
Yeah. Okay, I'm curious what this 3,000 very
Right,
exceptional.
right. Is that a crazy good unit, or it's a mismeasurement?
But yeah, I think that's actually a good point, because something that so far away from the distribution of all the others, yeah, it gives the sense that there's something.
And for
Yeah.
your bins, Davis, you did like
Mhm.
3 terciles. How did you do the bins?
The bins, let me see.
It would be helpful
I
to
think
just
it's
put the
just
lines
50.
here.
Yeah. Yeah, it's just starting assuming 50 bins and then
Okay.
kind of forcing
So some
everything.
of those we should see in the highest bin, perhaps, how that guy looks like.
Mm-hmm. Yeah.
You see it on the right too, like if I'm assuming these are the STD bars.
Yeah, so this is just a box and whisker plot. So
I see.
these,
So
yeah,
some
intercepts
percentiles.
IQR. Yeah. Mm-hmm.
Yeah, they're very large for sudden depth.
Mm-hmm. Yeah, because I'm not sure exactly how intuitively this might be a potential critique of this metric of how to interpret these negative log probabilities within the sliding window, and whether, once we have this score, um, how to interpret it more, like, I don't, yeah, like in an absolute versus just a comparative way.
Mhm.
Because it's like intuitively, I don't know what a 3,000 means. It just means something very big, I guess. But, or that session may have just had a very low mode baseline or something than the others that caused that, something that's maybe not that exceptional to show up very,
Yeah.
I'm not sure. So yeah, that's
I
one thing we
think
could look
it's
into.
worth checking if it's a mismeasurement or it's an accurate evaluation.
Yeah.
Yeah.
Yeah, I'll definitely do that. Um, yeah, and then, and maybe this is the same guy. You could check if they agree or disagree.
I was thinking, Davis, that would be also helpful in addition to, I'm sorry, I'm jumping a bit ahead here, but in addition to just showing the high, low, like the different bins, that we also take the ones that are good with one metric and bad with another metric.
Yeah.
And this is, so that way we can understand the metrics here better. But the key
Yeah, I
one
think
that
I have some. Oh, go ahead.
seems to be different is the Allen metric. The other two have at least a trend with the depth, but not the Allen metric. That's pretty interesting. Would be
That's
good
right.
to at least get some correlation, like between metrics, something to see which ones are more similar or different. Allen seems to be capturing.
The mesoscope, we adjust the power for each plane. So, I mean, there should be some depth component, but yeah.
Not as much.
Well, in the earlier plot, this 3000 looked like a mismeasurement to me. So I think it's worth checking that the distribution is, because there might be units that have a problem, so you're quantifying them properly, or units that are mismeasured by the metric, and so we just need to disentangle those.
Gotcha. Yeah. Okay. And
This is a
yeah.
lot more Gaussian, yeah, less
Mhm.
skewed.
Yeah, it seems very, very consistent measure.
Does that make sense? So this is the so this makes sense because you're measuring a statistics here, right? It's a p-value, right?
Yes, I think so.
Why do you
It's
say it's
very
a p-value?
because as I understand, it's measuring the distance between two distributions. Is that right?
Yeah. Hmm.
So you would expect less skewness, maybe?
I mean, it's the thing that caught my attention was that this one is skewed on the left, while the other ones were on the right. So here we have some really bad neurons, while the other ones said we have some really good neurons.
I think even though the lowest one is 65.
Well, in your distribution, it was all the way to 0.3. But I think
Oh,
a
that's
lot of
true.
this will become clear when we visualize some of these neurons.
Gotcha.
Okay.
Yeah, I think it's worth pulling out the
I think he has
outliers.
it. He has some of that analysis.
Down there? Oh, okay.
Yeah, if it is.
Sorry,
I
I
think
have one question about that score. I understood it that way that it measures the difference between the exponential and the Gaussian distribution, and I thought the exponential was expected for good reach ROI. So I would have expected that low values are good here, not big values. Am I wrong?
let me see.
I think that's right.
Okay, so it's combining two errors. Let me see. It's 1 minus the mean. Yeah, so it's the residuals. So yeah, it's using KS for both of them. So the higher the KS, the worse the score.
It's
Okay, so
one
yeah,
minus.
yeah,
Okay.
yeah.
Yeah, okay.
Mhm. Gotcha.
Okay.
Yeah, I had to double check that myself. Yeah. So yeah, the higher the yeah, and then gotcha. Okay. Yeah, so it's sort of combining both assumptions equally if as if they're both of equal importance, which is something I guess is open to interpretation, but I don't know if it'd be better to actually separate the noise assumption from the exponential assumption or to combine them together like that.
Could you say it again? What was the exponential assumption here? That's for the
So
calcium itself.
yeah, so if you have the event itself, the decay of that
Right.
the actual shape of the transient itself
Right.
matches an
And then
exponential.
this is the combination of both.
Yeah. And so
I
it's
see.
both that it's the taking that KS score for both of them, um, and then taking the mean of that, and then one minus that, and that's the score here. Um, all right. And so then this is kind of what you were talking about, Farzana, is the um, taking metrics that don't agree with each other. I think also I probably should have already done the outliers. I realizing that now. Um, but that this kind of gets whether if there's two ROIs or an ROI that has, a relatively good score but a relatively bad score in the other. What
It's
those
helpful, Davis, to also just generally show the pairwise correlation across neurons for pairs of metrics for each neuron.
Okay.
Yeah, or across neurons. So we see generally how they do you have, if you do a scatter plot or something. That's this, right? Nice.
Yeah. I mean, I guess
Cool.
it's not normalized, but it's just the raw
So
things for each.
Alan is doing its own thing, but these two, and that's kind of what we saw
Yeah.
from your box plots.
It's not very correlated.
The top one is
Mhm.
not, I would
Yeah.
call it more like,
And the bottom one is independent.
yeah.
Tough
But I
one.
think it's I would rather get to the plots of the traces.
Okay. Uh, uh, yeah. So this is one with a high exceptional event.
So just to
Um,
make sure, this is an example ROI that had
yeah,
high.
this is only a short snippet of it, but yeah. So
But
one that had a high exceptional event score.
so I guess can it be the case that would a cell that fire very briefly have a high exceptional event score?
No, I think
I think
because
it could
that's
be
about.
this, like these. It seems like this would. Um, well, yeah, I guess it depends on, it's because it's the sum of like a sliding
Yeah.
window of those log probabilities. So I think theoretically you'd only need one big,
No, but I
right?
think it takes into account how many. So it's not that if you just get like, let's say, a sustained trace of 10 high score values, then you get that. You need to have more than that. But
I think a good measure here is if we make an estimate of the noise across the whole session, like just a fixed value. I think this is what this is doing, no?
Yeah, it's using that mode, the half mode measure, um, that it described earlier. Yeah, for this one, while the other
Yeah,
one's using the median. Yeah.
I see.
Oh, and it only counts as noise, things that are below that half mode, in its calculation of like the noise. Um, yeah, so there's
one good way,
these.
because now you're just showing a snippet. I mean, it's randomly selected. That's neat. Well, it doesn't seem to be randomly selected for all of them. You're showing the same thing. But one way is to get the average calcium transients and show that, and then we can see, because this
Okay.
snippet for the top neuron may just be randomly chosen from a bad part of it.
Okay.
But the bottom is now good, right? So that makes sense. And I don't know if you did the average one that I suggested.
Let me see. So
Okay,
this one is not
some
in,
of the low ones are very clearly bad.
yeah.
That's good.
Yeah, so it seems like this one might be a good one for detecting poor ROIs.
Except for the first trace,
Uh,
which, I'm curious to know how it looked for the rest of it, but yeah.
Okay, and then now we're starting to get, these are the 95 50th ones. So this one has a high um, SNR. That's interesting.
Would have been helpful, Davis, if for each of these you had all the three metrics. So then maybe we
Oh, yeah.
conclude that we need all of these to be high. So if we see that this is, for instance, low on the other two, then we know
Mhm.
that if one is high, it's not sufficient.
I wonder if it will be constructive to separate the signal evaluations from the noise evaluation in each metric. So
Mhm.
so you because you can make a table with a signal is measured or noise is measured in each metric, and you extract that numbers
Okay.
and you sort of put it in the table for all of the metrics, and you extract the cells that have high noise, low noise for each of the metric, high signal, low signal, and then all of
Yeah.
them have a different way to compare both, but that might be easier to identify outlying cells because I think there are different ways. You could have a cells that have a high noise but very little activity.
But then how
Uh,
would you, I guess for this 9550 SNR, that would be easier, right? The denominator is the noise. But for Andros metric, there that's the whole thing is the noise estimate is used to identify those. So would you call that signal metric or no? Because that's a combined
well, I
metric.
think in Andrea, as I understand it, the noise is your background thing, and the signal is the exceptional event.
So you mean to
So
plot that
yeah, so
the
you
error
I think
function?
it's trying to say
Yeah,
how strong as the most the
yeah,
largest event during the recording compared to the noise
yeah.
estimate.
So we can output the error function output from that and then get the, yeah, possibly. Because I guess what you are getting at is that some of these traces that don't look good but have high values is potentially because the signal was noise, but it happened to have also very low noise, and that makes the SNR look good, even though the signal
Yeah, I
was.
mean, just I am just thinking about how to disentangle.
But then it
Uh,
becomes very high dimensional. So we have like for each of these metrics, we're dividing into two. Now we end up with 2 times 3, 6 metrics. How do we put them together?
yeah, I guess what are what is useful in your mind for a description of the data that we are sort of sharing?
I'm still waiting to see the rest of the plots that Davis had, but usually the way I do these things is that I get the upper tier side of each, then combinations. I come up, like I find the outlier cases, and then it seems like this combination is doing good, and then I set different levels. Like the most conservative level, I only get the ones that are good with all of the three or the other, and then I get the outcome and I see how they compare. So that's been my method. I guess at this point we're still not quite clear about how these metrics relate, but when the figures are shown, we'll know better. But I'm worried if we just keep adding more metrics, it can become.
Well, just stepping back, if we sort of maybe the goal here is to find the sessions that have the strongest signal and or the strongest responses with those metrics.
Yeah, I guess the goal is to find the neurons that if our eyes look at them and say these are good neurons, the metric can identify them. That's how I would say it. Like that top one, that's about there's something wrong with that matrix, something failed. So ideally, we will have much less of these false positives with whatever combination of metrics we end up using. I mean, we will have some of them, there is no way, but hopefully it will be less than 5%. So we can trust the majority of our good ROIs.
Just one question. I've been late, unfortunately. So how is signal defined in this context of this analysis, Davis?
Um, in this one, the 95th to the 50th, it's basically subtracting the median from the 95th percentile, and then taking a Gaussian smoothing and subtracting that from the original values, and then comparing. Let me double check I'm saying this correctly. Then yeah, so the signal is that 95th minus the 50th, and then to get the noise, we use the Gaussian smoothing and then subtract the original values from that. And then we take the median absolute. I guess you're asking how we get the signal aspect of it. So that's that part
Yeah.
of it. So yeah, it's sort of, so I guess it's the amplitude divided by the standard deviation is the ratio of the of that
Okay.
It's
signal.
only 15 minutes, Davis. Do you want to show the distribution?
Yeah, sorry.
Okay, thanks. Yeah.
Gotcha. And then, okay, so we were at, yeah, robust SNR. So I can keep going through these. Yeah, and this one is a low SNR. Some of these seems like it does a fairly good job of identifying those. And then I guess this is a little less, well, I guess a high event. So this kind of shows that these maybe aren't the best for identifying the DFF traces, the Gaussian fit score.
Yeah.
Let me see. Yeah, it seems like it's kind of hard to distinguish the low from the high ones at this one. And then I have the plots of the ROIs with that are binned into like low, medium, and high with averages for each metric.
But the average you did, so right. Well, so do you have a way to get the calcium transient from each of these? You should, right? Because the event identification will tell you where the events are, and then you can get the average of
Yeah.
those. And then that's what you, because the average of these, that won't be easy. So then you show for all the high value metrics of a certain, high values of a certain metric, what's the average calcium transient? That would help. Or if you want to take it to a different level, you can show the stimulus aligned traces and take the average for the high values of a metric versus low.
I still think that it will be easier to sort of introduce hot noise and hot signal and measure in the different metrics, break it down. Even for introducing the definition will be clear. And then because I think the goal of this analysis, I just step back, but it's to allow people to see really quickly, oh, can I find a session with really responsive neurons? Or what are the session with the strongest responsive neurons against the noise? What are the ones that are more difficult to analyze in that respect? And so like just to get a sense of that sort of distribution.
Okay.
So
yeah,
does that make sense?
Yeah, that makes sense.
I'm not sure it makes sense to me. Because what would you achieve if you get the neurons that have high signal but also high noise? What would you do with that? Is the goal not to identify neurons that we want to analyze that have good quality?
That's right.
So then a good quality neuron needs to have high noise, high signal, low noise. Why would you want to look at that? And then this is a simplified metric that looks.
Well, because I worried there are some cases where you might have high, very low noise, right?
Yeah.
And very low signal.
Yeah.
Because say the animal is doing is not attentive, or like, so you could have a low responsive because it's not about, it's about the units.
Yeah.
But
I see
isn't
what
it
you're
then
saying.
two things, Jerome? That one thing is kind of stimulus responsiveness, like let's say to the upper stimuli or so that are of interest, and then
Yep.
the other thing is just like the signal to noise ratio.
Yep.
So yeah, and then it helps. I mean, for signal to noise ratio, good definition of what the signal is. I think I like Fazane, I like the idea to go for event detection to figure out what is signal, because I mean these spike events are essentially the signal we're after. Maybe that helps to, because in this case, for example, there's in the medium bin, for example, in the lower, like the lowest one looks kind of fine, for example. Maybe with event detection, it's a bit easier to, I don't know.
I think it's all about like how simplified we want this to be versus how many more metrics. So if we're going to divide signal, the SNR into two metrics, then there are a lot more thresholds to be identified and to apply. But yeah, maybe we say that it seems to me like the Allen is not doing a good job here. So I don't think we should bother with that. So the combination of this and that could be doing well. It can be good to see when they contradict and what kind of traces we get. Also, we can do what you're saying, Jerome, that it should be high on these two, and also very small values of signal and very small values of noise should be avoided, even if it leads to a high SNR. But then we're just making it a bit more complicated to apply and define all these thresholds.
I wonder if what we are trying to, I mean, this is a bit of a brainstorming session, but I wonder if what we're trying to do is to classify the units in different buckets. And we haven't defined the buckets yet, but we're trying to sort of use boost metrics to sort of put units in different buckets that are relevant for different types of analysis.
Yeah, I think it's very helpful to have them. So in case someone wants to look at these separately, the signal and the noise, to provide it to them. I agree. But then this goes back to another conversation that we had here. Sarah was here, and I said that is it like we want to give the user also the good set of ROIs, or we want to leave it to them? So that's fair. If it is leave it to them, the more the better, and they can choose this. They decide. But if it is us also saying that this is a good set of ROIs, go and work with those, then it's like we have to come up with more thresholds as we increase the dimension of these metrics. It becomes harder.
But when we start doing analysis on this, don't we want to have those buckets?
Yeah, I think it's good to give the separate values and also the combined value.
Davis, do you feel like those metrics can be used to classify the units at this point, or is
I mean, I actually think the idea of breaking up the signal and noise measures is probably a good idea. If we get four, because if we can for any one, I guess, pair of um, signal and noise measures, we would get four potential combinations if we bend them into high, low. Um, like, and then maybe using that as a jumping off point, or well, yeah, because it seems like it's relatively easy to with these metrics to create something where if you look at like a low ranking thing, it tells you what ones are not performing very well. But the difficulty seems to being finding a metric that consistently identifies only good ones, if that makes sense. And I think that of what, at least with the ones that we're currently looking at. And if that sort of separation out that you're talking about, I think might help with figuring out, finding a method to where we can reliably kind of like bin them, or we could, if that makes sense. And I think that would be for the data release paper, then that would give us something that's easier to visualize across a lot of sessions, potentially. If we have those distributions.
We lost. Can you hear me?
Oh, I'm sorry. Did I mute myself? Or did
no,
I
no,
just talk?
my connection dropped. I don't know if it was on my end.
No,
Well,
it was good for us.
What about, I mean, it's 9:55. What about if Davis and Frozen and a couple others, you try to look at all of the outliers and the types of cells that are identified by those metrics, like the outliers and the one that are in the middle, and try to define those buckets based on signal and noise and SNR combined, and then do a first pass at classifying the cells in those buckets. Because I think that's what a figure could be, is you describe the metrics, how we classify the cells, and then you show how many cells we have in each bucket across the. Does that make sense?
Mm-hmm.
And so perhaps the first step is that you do a first pass at defining the buckets that make sense given the data you're seeing.
Yeah.
So, that could be a high responsive, high SNR cells, high low noise, but low responsive cells. Like, there could be different buckets. And once we have the bucket, once we agree on the buckets where we just count the number of units and we say, this is what we see across all the sessions we collected, how many of each buckets.
So my suggestion is the following. He uses the events to get an average calcium transient for each neuron. And that becomes our way of evaluating the quality of a neuron, because the average calcium transient, if it doesn't look good, then the events, well, it's a bit mixed with event identification, but let's say we trust our event identification. So that's how you summarize a 1 hour session into a few frames, which are called the average calcium transient. Then you have the distribution of a metric for all neurons. You set different bins. You set different thresholds. You go using this threshold as good, bad. You get the average calcium transient of all neurons called bad using that threshold. You keep sliding it in a reasonable way, not too tedious or not too loose. And then you see at what threshold you seem to be dividing reasonably good and bad neurons. And then you do it for the other metric. I would just avoid the Allen metric. That didn't seem to be good, the two metrics. And then we see, is it a good combination, or do we have a good recommendation for the threshold here? And that's how we find these buckets. Otherwise, Jerome, how would you find a good and bad bucket? We need to define a threshold here. And the way to do it, yeah.
I think what you described makes sense.
The other
Seems
way
like a
that
reasonable process.
The other way that we're doing in my lab, and it's more tedious, is that we're doing one by one through neurons. We have the matrix, we go one by one through them, we identify what's good, what's bad, and then that helps us the manual identification. Now we go and look at the metric values, and this is now how we come up with a good threshold. So, but that would be it
But
needs someone.
We don't necessarily need to have like a golden threshold that is miracle. It just have
Then
to
how would you
be,
define?
at some point, it's just a trade-off.
Yes, for sure, yeah.
But I think what's important is that we use the same threshold across all sessions so that you get a good measure of distribution.
I mean, one idea would be that just how we train data set, like there would be a subset of sessions that this manual tedious work is done, that ground truth manually called good,
Oh.
bad. Then we use those to define the threshold, but this is like, it depends how much we want to do this right. The other is the way that I said, that we just get an average calcium transient and we kind of use that as a bulk measure of, is this threshold good or bad?
I think this makes sense to me. The starting from the event size.
Average, yeah, that would be my suggestion too. Yeah.
Yeah. Do you want to try to take a stab at this? I also I'm gonna spend a little more time rereading those metrics to get a better sense of how they compare one another. I don't think I completely built my mind on it. Okay.
And if you have, Jerome, suggestions for other SNRs, that would be great.
Yeah, no, I'm happy to follow your lead, Farzaneh, there. But
Thanks,
I'm
well, I mean,
happy
like,
to
if you've seen
provide inputs.
Thanks. But I'm saying, if in some papers or in some other work you've seen other SNR metrics, like, please let us know. This was a starting point for us.
Oh, Lucas is making a suggestion. I think it's probably, is it Peter Ruprecht's work?
Yeah.
Yeah. We could ask him his opinion. Now we've been in touch with him actually.
Is it Cascade or is it?
Yeah.
Yeah.
But well, we're not using this toolbox at the moment.
Yeah. So I think the idea is to use what Alan is doing. I don't think we are doing the event detection here.
Okay.
Otherwise,
Is
that will
10
continue. Yeah.
is 10 is next week a good time to discuss this again, or do you want more time?
I think it should be relatively easy because all of the events are already pre-calculated. So I just have to write code to take them and average them together, the area around the transients, which I don't think with AI should not be too hard to do.
We have it
Okay.
also, it's already done, Davis, for other
Okay. Yes,
projects.
Ali
So you
already
can
have
just, exactly, yeah, so you can just
Okay.
use that.
And then we try to sort of discuss next week how we want to define the bucket. Or, you could take a first stab at it and then we sort of iterate on it. Because again, the intent, the way I see it, where is my window?
Oh, I can stop sharing too if you want.
I just want to bring this up. In my mind, we'll have like, because this figure 4 is, maybe I could take a stab at sort of fleshing it out a little more clearly. But what I had in mind is that you have like a define the metrics, and then from the metrics you show the different examples of types of cells, and so then you define your bucket, and then the second row is distribution of the bucket across session, and so we'll have to do the same for eFizz and SLAP2, but let's hold off onto this until you have converge.
And what is the response amplitude here?
Well, but in my mind, the signal is the
The
signal
signal.
distribution, right? So the amplitude, how responsive the cells are.
You don't mean to the stimulus. You're saying in general the.
Well, we can't disentangle because
Yeah.
all the sessions have a stimulus, so there's
That
always
could be
good.
the calcium transient. So maybe that's that could be that, to show the
Yep.
average calcium.
Yeah, we have to make a proposal for this figure. I could bring this next week, like a proposal for the, with just boxes with description.
Sounds good.
Okay. Well, I think we've covered what we wanted to cover.
Oh, sounds good.
And then we'll return to this discussion next week.
Thanks, Davis.
Okay.
Thanks all.
Thank you.
Thank you. Thanks for the feedback, everyone.